We're working through Limits Chapter 1, Morning Review, number 3. So number 1 here, we want to evaluate the limit. So whenever we want to evaluate limit, first thing we do is we just plug in the target x value and see what we get. Here, if we plug in 0, we're going to get 0 over 0. And if we get 0 over 0, we know that there's a hole in that's preventing our answer to show up immediately. So we have to work to see if we can simplify the expression so that we can reevaluate the limit. So this is a problem where we can use the conjugate method, and usually conjugate, we multiply by the conjugate of the denominator, and usually that will help rationalize the numerator. But in this case, we're using the conjugate method to help us simplify the numerator expression to allow us to find a different form that will hopefully cancel out this x in the denominator that's causing the denominator, or causing the expression to be unable to be evaluated. So we're multiplied by the conjugate of the numerator. So the conjugate will be the same two terms as what we see here. Just have to change the sign. So negative here, so we have to make it positive. And because we don't want to change the overall value of this expression, whatever we do to the numerator, we're also going to do to the denominator, which in essence will mean that we're just multiplying by 1, really. So we're not changing the value of the expression. So here, if we look to expand the expression, so if we distribute the terms through, the first two terms will multiply to be 2 plus x. The middle and the outside terms will cancel out, and the last terms will multiply to be negative 2. 2 minus 2 is 0, and then the x over x will cancel out to be 1 in the numerator over square root of 2 plus x plus root 2. Once this x goes away, then we can reevaluate the limit, plug 0 into the remaining x, so root 2 plus root 2 is 2 root 2, so 1 over 2 root 2 is the limit. Okay, number 2, for x does not equal to 4, the function h of x is equal to x squared plus x minus 20. What value should be assigned to h of 4 to make h of x continuous at x equals 4? So what we can do is, if we can find out the limit of this expression, then we know where the graph is headed towards on either side of 4. And will allow us to figure out where the hole is. So once we know where the hole is in the graph, then we can fill in h of 4 to close up that hole and therefore make our function continuous. So x can be equal to 4. So we know that on either side of 4, however, the graph will connect on both sides of x equals 4. So if we find the limit, then we know where the hole is. So limit of our expression as x approaches 4. So if we plug 4 in, we're going to get 0 over 0, which means that we can continue to factor and simplify. If we factor the numerator, we get x plus 5 times x minus 4 over x minus 4. The x minus 4 reduces, and if we reevaluate the limit, we get x 4 plus 5, which is 9. So 9 represents the y value of the hole in the graph. So the hole is existing at the y value, or at the order pair of 4, 9. And if we define h of 4 is equal to 9, then we can fill that hole in, which will therefore make our function continuous. Number 3, we have a piecewise function, x squared minus 2 to the left of 0 and 3x plus k to the right of 0. Find the value for the constant k that will make the function continuous. So if we want the function to be continuous, then we just need to know what y value each branch is approaching on either side of 0. So we can find the limit as x approaches 0 for the first term, for the first expression, and do the same for the bottom expression. Or we can do is we can set the two equations equal to each other and figure out what the k value is when x is 0, because we know that we need these two graphs to meet at x equals 0, and then we can find out what the value of k that will cause the two expressions to have the same y value. So if we set them equal to each other, replace x with 0, because we know that we want these two graphs to connect at x equals 0. So we get 0 minus 2 equals 0 plus k, so k equals negative 2. So therefore, when k is negative 2, then two graphs are equal. So the function, piecewise function, is therefore x squared minus 2 and 3x minus 2, since k gets replaced with negative 2. All right, let me just quickly go over number 4, because number 4 is an omitted problem because of the messy algebraic steps. But essentially, we're trying to find the values of a and b so that our function is continuous everywhere. If the function is to be continuous, then we want the left branch to connect to the same y value as the ordered pair, and therefore connect to the right branch. So we need all these three functions to share the same y value at x equals negative 2. However, we see a lot of variables here that we have to deal with besides the x. So we have a and b. So what we can do is we can set the first two piecewise equal to each other, because we know that when these are equal at x equals negative 2, that we know that has to be true. They must share the same y value at negative 2. And then we can do the same systems of equation for the second piecewise function, for the second and third piecewise functions. And then using systems of equations, we can solve one variable at a time that way. So if we set the two equations equal to each other, the first and second equation equal to each other, replace every x with 2, then we can get our way down to 13b plus 12a plus 2a is equal to 0. On the others, for the second and third piecewise, we can set the two equations equal to each other, the second and third equation. We know that x equals negative 2 as well is where these two, where the point and the graph will meet. So replace x with negative 2, and then we're down to negative 3b plus 8a is equal to negative 11. So we have two variables, but we can put them on, we can line them up and then distribute through, so we can cancel out one variable and solve for the other variable. So it looks like b, if we solve for b first, is 1/5, and once we have 1/5 for b, then we can plug into one of the equations to solve for a, which is negative 13 over 10. All right, number 5 here, we have a continuous function, so no breaks in the graph. So we have selected values of f given in the table below. So we have these ordered pairs here, which I'm going to go ahead and just plot onto our graph. What is the least number of solutions that f of x equals to 1/2 on the closed interval from 1 to 8? So it's saying, what is the least number of times that the graph will cross the y value of 1/2 between these graphs? So there may be, there may be more than crosses, crossing of y equals 1/2 between these intervals, but we're looking for the least number of times. So if we just plot all these ordered pairs, then we can see, in order to connect all the points, how many times does the graph have to cross y equals 1/2. So here I have an ordered pair below y 1/2. Here I have an ordered pair above. Here I have one below, and I have one above. So in order to connect all those points, we know that we have to cross at least 3 times. The graph will have at least 3 solutions with y equals 1/2. And this is due to intermediate value theorem, because we know that if we have endpoints on either side of our target y value and the graph is continuous, the graph has to cross through that y value somewhere between that interval.